Okay. Alright, quiet down. We've done limits and continuity, so the worksheet I have for you today is going to kind of review some of that stuff. But also there's another concept, now that you've done derivatives, and what does the derivative represent? The slope of a curve, or slope at a point on a curve, right? Yes?
Why don't you start your reporting about like stages?
Okay, so today we're going to talk about something called differentiability. That's a tough one for me. Okay. Differentiability. Okay, this means differentiating something in math is the same thing as doing a derivative. Okay, that's what differentiating means in math. Okay, or in calculus. So differentiating means doing derivative. So differentiability means if something is differentiable, that means you can do a derivative of it. Okay? Means you can do a derivative. Or it means there exists a slope. Okay? So you can do a derivative, which also means that the slope exists. Okay? Alright. So, hey, you guys stop and pay attention. Alright? First of all, if something is differentiable, it automatically has to be continuous. Because if something is not continuous, then there's no slope at a point where it's not continuous. Alright, so we'll do some examples of that. But a function must be continuous to be differentiable. Okay? So we're going to basically make a list of things that would make a function not differentiable. Okay? And then everything else would be differentiable. Alright? So first of all, so let's say not differentiable. Let's talk about the continuity thing first, because remember, for something to be differentiable, it has to be continuous. So if something is not continuous, it's not differentiable. Alright, so where's a function not continuous? A jump, okay? So, whatever, any kind of jump. Since it's not continuous there, it cannot be differentiable there. Okay? What else? Where's something else? A hole, alright? A hole, or removable discontinuity. That is also not continuous, so it can't be differentiable. Okay? We had another one that's not continuous. Anybody remember? Third. A vertical asymptote. Okay? So a vertical asymptote, because that's going like this. Okay? So a vertical asymptote is not continuous, so it's also not differentiable. Okay, so those are the ones that deal with the continuity. But there's actually some other situations that are not differentiable. Okay, but that are continuous. So these are not continuous and not differentiable. These ones I just did. Okay, if they're not continuous, they're automatically not differentiable. Okay. Now, there's some other stuff that's not differentiable though, which if you have a corner a corner is not differentiable just at that corner. Okay, this is differentiable on the lines next to it, but it's not differentiable at the corner. And the reason why is because you have a slope. You have a slope here. Okay, and this would be a certain slope, and then the slope suddenly changes to a different slope, and there's no intermediate there if it's a corner, it's a sharp corner. So at that corner, there actually is no slope. Okay? There's no slope at the corner, so it's not differentiable. The same thing happens with something like this, is called a cusp. It's just like a corner. Same reasoning. Okay? The slope suddenly changes, and so at that point where it changes, there is no slope. Okay? And I think that's about it. Corner cusp. So, I think that's about it. So these two things are continuous, right? Because there's no hole or anything, but they are not differential.
So it's like the top of a parabola, like it goes upside down, considered a corner.
No, because that's smooth. That's smooth. As long as it's...
There are points that you can around.
Yeah, but that's okay. That still has a slope because it's smooth there. So really, you can kind of think of differentiability as being smooth, because that way, if you have the question was about the top of an upside down parabola. If you have the top of an upside down parabola, okay, it looks like that. Well, all of these, as long as it's, you guys listen, as long as it's not a sharp corner, you have slopes everywhere the whole time, okay? You have every slope there, and so it doesn't the slope never immediately changes. It never immediately jumps from like a positive slope to a negative slope. It transitions smoothly all the way, okay? So there's slopes at every point there, all right? So it's only when it's a sharp corner or cusp that, that it would be not differentiable, okay? Let me look at this. Okay, let's talk about piecewise differentiability. So you guys have done piecewise continuity. Anybody remember how to do that? I'm not going to keep spelling that out, okay? So. It's silent anyway. Who cares? All right. So let's say we have f of x equals x squared plus 4 for x is less than 3, and 19 minus 2x for x is greater than or equal to 3. Okay, so for piecewise differentiability, remember, differentiable implies continuity. So you would check continuity first anyway, because if it's not continuous, it can't be differentiable, right? So you check the continuity first. How do you check continuity on a piecewise? You plug in the 3 and see what? If they're equal to each other. If they are, then it's continuous, right? So if we plug in 3, so for continuous, we're going to plug in 3, and we're going to get the top is going to be 9 plus 4, and the bottom is going to be 19 minus 6. And look at that, those come out the same. So that is continuous, right? Okay, so to check if a piecewise is differentiable, anybody have a guess as what we're going to do? What does differentiability have to do with? Do what? Smoothness, or, yeah, it's derivatives, right? So for something to be differentiable, it has to have the same slope coming from both sides, okay? Or in other words, you would do the derivatives of both lines, okay? So differentiability, so that's how you spell that. Differentiability. We're going to do the derivatives of each line, okay? So the derivative of the top is what? 2x. The derivative of the bottom is -2. Okay, we're going to plug in the x again. So this one is 6. There's nothing to plug in on the second line here, so it just stays -2. Now, are those the same? No. So this is not differentiable. So this piecewise function is continuous, but it's not differentiable. You're still plugging in this same x, this 3 over here. Okay? So this, whatever's on this side, whatever these domains are, this is listed over here as your x greater than, that's always what you're plugging in, for continuity and for differentiability. But for continuity, you plug it into the originals the way they are. For differentiability, you plug it into the derivatives and see if they come out the same. Okay? So this would be yes, this would be no. So if it's continuous, but not differentiable, what must be here at 3? A corner or a cusp. Okay? That's the only way you can have something that's continual but not differentiable. Here's a parabola. This is a parabola. This is a line. So is it a corner or a cusp? It doesn't really matter. It's either one. It'd be a cusp because part. Okay. Okay, I think that's all we need for today. Good?